Hello students, so today we will discuss about uh, photonic crystals. Now, photonic crystals are mainly ordered nanostructures in which there are two media. So we can define it by say there are ordered nanostructures and there are two media with different dielectric constants or refractive indices. Media with different dielectric constant or refractive indices, and they are arranged in a periodic form. And in other words, they form two interpenetrating domains that form two interpenetrating domains one of higher refractive index, other of lower refractive index. So higher and lower refractive indices. Now, in a photonic crystals, for a certain range of energy of photon, certain range of energy of photon and certain range of wave vectors k, light is not allowed to propagate through this medium. So around certain range, light not allowed propagate through this medium. And if you generate light inside it, it cannot propagate in this direction. So light is generated inside a photonic crystal, then there is a direction through which it cannot propagate. In a certain direction. And lastly, if we send light from the outside, it gets reflected. So light from outside gets reflected. So there are three important features. Firstly, it is not allowed to propagate in a certain direction if it is inside the crystal, and also if a light is coming from the outside, it is getting reflected. So these three for a certain range of EPH and wave vector. Now if you take a plot of transmittance with respect to and reflectance. So it is transmittant percentage, then it will show a certain dip like this, and if we take the reflectance percentage, it also will show like this. It is between 500 to 1200 nanometers wavelength. So if it is for this 500 to 1200, that is means the visible region. So now these photonic crystals are produced by close packing of polystyrene spheres. Close packing of polystyrene spheres. There has to, as I said, there are two refractive indices, N1 and N2. If the ratio between them is large, it has to be maintained large, so a proper shape of building blocks need to be maintained. The wave, the band gap again is not dependent on the direction of wave vectors. Not dependent on the direction of wave vectors. We define slide propagation, and the density of the photon state goes to 0 in the band gap region. So density of photon states it goes to 0 in the band gap region. So these materials are called photonic crystals, or often called photonic band gap materials. But for the 3D arrangement, if you look into the 3-dimensional arrangement, so of say polystyrene spheres, so it has PS spheres, it looks something like this. Spheres are arranged in this fashion. And these spheres are made by colloidal chemistry, and therefore also called colloidal crystals. The 2D, on the other hand, is actually a stack of cylinders or parallelograms. Stacks of cylinders or parallelogram grids like this, stack like this. say is a refractive index N1, and the gap between them is N2, which may be air. And examples of these are the photonic crystal fibers. Photonic crystal fibers. And lastly, if you look into the one-dimensional arrangement, so you can consider it to be an alternate layers of different n. Layers of different n. This can be a first layer. Then this can be refractive index N1. This is N2. So there are alternate layers. It forms a one-dimensional photonic crystals, and the variation is along the vertical axis. So that's stacking. And refractive index variation along only the vertical axis. Along the vertical axis. And a good example is of Bragg grating. Good example. Now these are the three different types of photonic crystals. Now as we have reciprocal lattice in the case of normal crystals, atomic crystals, similarly we do have a reciprocal lattice for the photonic crystals as well. So the reciprocal lattice for a 3D arrangement of photonic crystals is shaped like this. This is for 3D. This is for 2D. And this is for 1D. Now, the 3D photonic crystals are also called the opal structure. And in these, the band gap is not a full band gap, as the density of photon states do not go to zero at band gap. As density of photon states don't go to zero at band gap. Now one needs to inverse structure with voids of higher refractive index and packing units of low refractive index. So, and one approach to form an inverse opal if packed spheres are hollow and n is equal to 1. So we are trying to make the inverse opal structure, so it can be done by, if packed spheres are followed, the packed spheres are hollow refractive index is equal to 1, and another refractive index surrounding them, maybe smoother one. It varies from 2 to 9 in fact. Now another way of polystyrene spheres is that is the fill interstitials with gallium arsenide. And then the polystyrene is burned to leave a hole. This way this can be done. And if silica spheres are used, they can be etched to produce inverse wall structure. On the way, if there are silica, they can be etched to produce the inverse wall structure. So the basic concept is that when you are dealing with a 3D arrangement and you have these polystyrene spheres arranged in 3D arrangement, and you would like to make an inverse, so you somehow need to replace these polystyrene spheres with something with holes. That means you need to put something in between where there was initially air. You need to increase the refractive index of that medium, whereas you need to decrease the refractive index of the polystyrene sphere medium, and by etching away the higher refractive index. So if it was N1 and it was N2, where N1 was greater than N2, you need to, in the inverse structure, it should be the opposite thing. It should be the N1 should be less than N2, where we have replaced etched away, like in this case, we have burned the polystyrene spheres to form a hole, whereas the air has been replaced by the higher refractive index material. So that's why you get an opal structure, not inverse opal structure.